This video considers what happens if you have longer input horizons. In the previous video then, we've demonstrated through a number of examples and simple argument that if you have an input horizon of 2, it improves on what you might get with an input horizon of 1, but it's not necessarily the best you can do. We've got similar conclusions with both nu equals 1 and nu equals 2. That is, in general, if you had low output horizons, the optimization does not reflect enough of the predicted behavior to be meaningful, so that's something you can't do. If you had high output horizons, the steady state error dominates J, and thus the steady state prediction tends to go to the correct value, and then you've only got 1 degree of freedom left in order to optimize the rest of the behavior. And that's why in many cases nu equals 2 was insufficient to give good predictions. If you've got systems with undesirable open loop dynamics, and that could be an unstable process or oscillation or something like that, then nu equals 2 is often insufficient in terms of the flexibility it gives you to shape the trajectories to give you the predictions that you want. So what we're going to do in this video is we're going to say, okay, let's look at what happens with several different possibilities for nu, and we'll look at them all simultaneously so we can get an idea of whether there's a pattern and some generic understanding or insight. Just a reminder that we're assuming that the feed forward is a constant. Here's the first example then, and you'll notice what we've done is we've overlaid the responses for a number of different values of nu. You can see then, with a choice of nu equals 1, the predictions aren't particularly good. Here we've got an output horizon of 5, which is short. If we choose nu equals 2, things are better. If we choose nu equals 3, things are slightly better, and so on. But remember, because we've got a short output horizon, all the emphasis is focused within here, and there's no weighting in the optimization on what happens to the predictions beyond. So you could argue that you've got better performance within the prediction horizon, but actually what's happening in the longer term is not necessarily very good anyway. And that just reiterates the point that if you've got low output horizons, don't expect the optimization to give you a sensible result. I've extended the output horizon then here so that we can get a better view on what happens as you change the control horizon. And here you can see fairly clearly if nu equals 1, performance isn't too good. But once you get to nu equals 2 and above, the predictions aren't too bad. And what I've said is once you get above 3 or above, you tend to find that the predictions are almost the same. They're obviously not exactly the same, but they are fairly similar. And therefore, you can see that as long as I choose nu greater than or equal to 3, I'm likely to get fairly good predictions, and therefore my optimization is likely to be fairly well posed. If you look at the inputs that you're getting for this system, again you'll see nu equals 1, this prediction, nu equals 2, this prediction, but once you get to nu equals 3, 4, 5, you see that the first few values are pretty constant, and therefore increasing nu beyond that value makes little difference. Just to show you the final thing then, what we've said is you can one check for whether your optimization makes sense is you overlay the optimized open loop prediction with the closed loop behavior that results. And if the two are similar, you're confident that your optimization made sense. If the two differ, then it means you keep changing your mind, and therefore your optimization wasn't very well posed. And here you can see with the choice of ny equals 20 and nu equals 5, it's very difficult to spot a difference between the optimized prediction and the closed loop behavior that's resulted. And therefore I can be confident that my optimization is well posed and is going to give me robust and sensible results. Let's look at a second example then. Example 2, you'll remember, has a non-minimum phase characteristic. And again, for completeness here, I've started by just doing ny equals 5. And in this particular case, what you can see is that as nu increases, the performance actually gets worse. And that's because of the non-minimum phase characteristic in combination with a low output horizon. And you can sit down and look at it and you can say, I understand why it makes things worse. So I'm not going to dwell on that because we know the output horizons shouldn't be short. If I choose the output horizon to be longer, so here let's take it to be something like 20, then you can see that as I increase NU, the performance gets better. So the predicted performance gets better and better as I increase NU. And you'll notice here that once I get to about NU equals 5, I'm not expecting much improvement in performance and beyond. You'll see within the prediction horizon, it's got a nice shape, it gets to the steady state, and there's only a very small offset beyond the prediction horizon. And you'll see what I've summarized at the bottom. Although NU equals 5 is clearly the best result here, you could make an argument that once you got above about 3, the predictions are reasonably constant. Here's the inputs, just if you wanted to look at them. And again, you notice with NU equals 1, you got that. With NU equals 2, you got that one. But once you got to NU equals 3, 4, and 5, the critical thing is the first control move was the same in all cases, and therefore once you introduce feedback, you'll find out that the closed loop responses are not a lot different whether you use NU equals 3, 4 or 5, even though you can see a more obvious difference in the open loop predictions. If I plot now the closed loop, and here I've gone a bit to town here, I've said I'm going to choose an output horizon of 25, an input horizon of 6, and you can see that the optimized predictions and the closed loop behavior that results are almost identical. So this suggests that my optimization is well posed and I can have confidence in it. Example 3. This was the example which has an open loop unstable pole. And again, if I choose a low output horizon, you see I don't get sensible results, so I'm not going to dwell on that. If I choose a higher output horizon, you'll see a similar pattern to what we've shown before. With NU equals 1, clearly it doesn't work, and we've said that before with the unstable open loop process. But in this particular case, the differences between NU equals 2, 3, 4, 5 are relatively small over the prediction horizon. So in this case you might get away with NU equals 2 and find that it's pretty much equivalent to the higher ones. If you look at the inputs, again, what do you notice? If NU equals 1, there's the first move, not very good, but for NU equals 2, 3, 4 and 5, you see the first move is fairly similar in all of these cases, and the overall trajectory here is fairly similar in all of those cases. If we look at the closed loop responses, and again I've gone to town a bit just to be on the safe side, NY equals 20, NU equals 5, and you can see that the optimized predictions pretty much match the closed loop behavior that follows. So again, this suggests our optimization is well posed and we're going to get good closed loop behavior. Final example then was this open loop system which had oscillatory modes. Now again, we've shown NY equals 5 for completeness, and you can see it doesn't matter what you do with NU, you're not going to get good behavior because the output horizon is too small. So increasing NU doesn't really help in this case. However, if I now take the output horizon up to 15 and start increasing the input horizon, what do you notice? NU equals 1, not very good. NU equals 2, not very good. NU equals 3, not particularly good. But once you get to NU equals 4, you see that the responses are dramatically better. You're not going to remove this oscillation altogether, it's got an oscillatory open loop mode, but you can damp it significantly. And what you can see here is once you get above 4, the responses become reasonably consistent. You've got very small steady state error and you've got good behavior within your horizon. So in this case, increasing NU has had a good impact, and the reason it has is because NY is large enough to observe and compensate for the open loop dynamics. And here you'll see we noted we need NU greater than or equal to 4. And in case you haven't been recollecting, you'll remember that the NU we needed has been different for each of these examples. One example, we found that 3 was about good enough. The unstable example, 2 was probably good enough. Here we need at least 4. So the input predictions settle if NU is greater than or equal to 4. And again, you can see there's NU equals 1, there's NU equals 2, there's NU equals 3, and clearly, once you get to 4 and above, you can see they're all pretty much following the same shape. And that's something you can use to say, okay, that's a big enough NU, because the shape of the input trajectory has pretty much settled once NU has got to 4. Again, if we overlay the open loop predictions and the closed loop behavior with some largish horizons, you can see there's very little difference between the two, so my optimization is well posed and I can have confidence that I'm going to get good closed loop behavior. Some observations then. The use of low output horizons, even with large NU, very rarely, and I'm not saying never, but rarely gives rise to sensible predictions. The optimization results from such a scenario cannot usually be trusted and should be avoided. So basically what I'm saying is I wouldn't ever use a low output horizon because I wouldn't be able to trust it. If you have a long output horizon and you combine this with a larger input horizon, you get better predicted performance, and generally speaking, if you've got good performance both within the horizon window and beyond, this is an indicator of a well-posed optimization. And you'll notice we've made the caveat that if you've got an unstable open loop process, you have to be careful. The examples shown here have shown that the first input value, the differences in it were minimal if NU was around 3 or greater. Now, I'm being simplistic there, and we're going to go back into this in the next video, but often a value of NU around 3 is good enough to give you enough flexibility in the predictions in order to get the predictions to be close to the behavior you really want. However, occasionally you might need a higher NU, and we'll give you some examples in the next video, and you will ultimately have to do some trial and error to identify how big does NU need to be. We haven't yet looked at the impact of changing the weights on the input. We did indicate that slightly in the previous video, so the next video is going to look at this in more detail and try and draw everything together and say, how do we come up with a choice of output horizon, input horizon and weights that mutually work together to give us a well-posed prediction.